Hello there, and welcome to Science for Sleep, where complex currents become gentle streams and electromagnetic mysteries drift softly into dreams. Tonight's peaceful journey explores something that surrounds us completely, yet remains wonderfully invisible: the gentle hum of electricity. It flows through your walls, dances in your devices, and quite literally sparks the thoughts in your mind right now as you listen. But before we begin untangling these invisible threads of power, I'd love to know, what's the last thing you plugged in today? Was it your phone settling in for the night, a bedside lamp casting its warm glow, or perhaps the very device you're using to hear these words right now? Fitting, isn't it? Here we are, using electricity to explore electricity like fish discussing water. If you find tonight's electrical expedition soothing, enlightening, or just a pleasant way to power down after a long day, I'd be ever so grateful if you'd give the video a like and perhaps subscribe. It helps this little corner of calm reach others who might need a peaceful pause in their own circuits. Now, I do hope this journey is fascinating enough to engage your mind, but gentle enough to let it drift when ready. After all, even electrons need their rest, though as we'll discover, they never really stop moving, the restless little things. So dim the lights, electrically powered of course, settle into your favourite spot and let's begin. Because somewhere between the wall socket and the stars, between lightning bolts and heartbeats, lies the story of the invisible force that powers nearly everything in our modern world. And what a quietly spectacular story it is. Have you ever really thought about what happens when you flip a light switch? I mean, really thought about it. One moment, darkness. The next, light. It feels like magic, doesn't it? This instantaneous response to the smallest gesture of your finger. But what's actually happening in that fraction of a second is far stranger than any magic trick, and infinitely more wonderful. Let's start with what electricity feels like, because that's how most of us first encounter it. Perhaps you remember being small, shuffling across carpet in fuzzy socks, reaching for a doorknob and zap, that tiny lightning bolt between your finger and the metal. Or maybe you recall the first time you felt your hair stand on end after going down a plastic slide, each strand reaching skyward like it was trying to escape your head. These moments, startling and sometimes amusing, are our earliest introductions to the peculiar personality of electricity. But what electricity feels like and what it actually is, well, those are rather different stories. If you could shrink yourself down, smaller than small, tinier than the tiniest speck of dust, smaller even than a single atom, you'd find yourself in a world that seems to follow entirely different rules from the one we inhabit. Here, in this subatomic realm, you'd meet the true stars of our electrical show, electrons. Electrons are peculiar little things. They're so small that if an atom were the size of a football stadium, an electron would be smaller than a marble. And not just any marble, but one that never stops moving. These tiny particles carry what we call negative charge, though calling it negative is really just a historical accident. We could just as easily have called it purple charge, or Tuesday charge. The name doesn't matter nearly as much as what it does. What makes electrons special, what gives them their electrical personality, is that they're social creatures with very specific preferences. They absolutely cannot stand being near other electrons. They repel each other with a determination that would impress even the most stubborn cat avoiding a bath, but show them a positive charge, like the kind carried by protons in an atom's nucleus, and they're drawn to it like moths to a flame, or perhaps more aptly, like tired listeners to a comfortable pillow. This push and pull, this eternal dance of attraction and repulsion, is what creates everything we call electricity. Every spark, every current, every glowing filament is really just electrons moving according to these simple rules. But oh, what complex and beautiful patterns emerge from such simple beginnings. In most atoms, electrons orbit the nucleus in a dreamy, probabilistic way. I say orbit, but that's not quite right. It's more like they exist in cloudy regions of possibility, sometimes here, sometimes there, never quite pinned down. It's as if each electron is playing an eternal game of hide and seek with the universe, and the universe can never quite catch it in one spot. This quantum fuzziness might sound like the electrons are confused, but they seem perfectly content with their arrangement. But here's where things get interesting. In some materials, we call them conductors, the outermost electrons aren't particularly attached to their home atoms. They're like social butterflies at a party, happy to mingle and move from atom to atom. Metals are particularly good at this. Copper, silver, gold. Their electrons flow like a gentle river when given the slightest encouragement. This is why we use copper wires to carry electricity. The electrons in copper are remarkably sociable travellers. In other materials, insulators like rubber, glass or plastic, the electrons are homebodies. They stick close to their atoms, refusing to budge no matter how much we might encourage them. This is why you can safely hold a wire by its plastic coating. Those insulator electrons form a sort of electron-proof barrier, keeping the flowing charge safely contained. And then there are the in-betweeners, the semiconductors like silicon. These materials can't quite make up their minds. Sometimes they conduct, sometimes they don't, depending on the conditions. It's this wishy-washy behaviour that makes them perfect for computer chips and solar panels, but we'll save that story for later. The ancient Greeks, clever as they were, actually noticed electricity long before anyone knew about electrons. Around 600 BCE, a philosopher named Thales of Miletus discovered that if you rubbed amber with fur, the amber would attract small objects like feathers or bits of straw. The Greek word for amber was electron, which is where our word electricity comes from. Imagine that. Every time you turn on a light, you're using a word that originally meant fossilized tree resin. Language, like electricity, follows some wonderfully winding paths. What Thales had discovered was static electricity, electrons being rubbed off one material and onto another. The fur lost electrons and became positively charged, while the amber gained them and became negative. This imbalance created an invisible force field that could reach out and pull on lightweight objects. It was humanity's first deliberate creation of electrical charge, though I doubt Thales imagined it would one day power devices that could show pictures of cats from the other side of the world. Static electricity might seem like a party trick compared to the electricity that powers our homes, but it's actually the same phenomenon, just dressed differently. The shock you get from a doorknob is electrons jumping through the air to balance out a charge difference. Lightning is the same thing on a magnificent scale. The electricity in your walls is electrons flowing in a controlled continuous stream rather than jumping all at once. Same actors, different choreography. What's particularly delightful about electrons is that they're everywhere. Every atom in your body contains electrons. The chair you're sitting on, the air you're breathing, the device playing these words, all of it is filled with electrons doing their eternal dance. In most cases, the positive and negative charges balance out perfectly, so we don't notice any electrical effects. It's only when we create an imbalance, when we convince electrons to move in concert, that the magic begins. And move they do, though perhaps not in the way you might imagine. When you flip that light switch, you might picture electrons racing through the wire at tremendous speed, zooming from the power plant to your light bulb like tiny Formula One cars. The reality is both slower and faster than that. The electrical signal, the wave of the influence that tells electrons to start moving, travels at a significant fraction of the speed of light. But the electrons themselves, they drift along at a pace that would make a snail look speedy, perhaps a few millimeters per second. How can the light turn on instantly if the electrons move so slowly? Think of it like a tube full of marbles. Push a marble in one end, and a marble pops out the other end almost immediately. You don't have to wait for that specific marble to travel the whole length. The push itself travels through all the marbles nearly instantaneously. Electrons in a wire work the same way. The electrical energy flows quickly even though the individual electrons drift along at a leisurely pace. This is just the beginning of electricity's strange and wonderful story. We've met our main characters, those restless social electrons, and seen how their simple rules of attraction and repulsion create the phenomena we observe. But knowing the dances is only the first step to understanding the dance. The real wonder comes when we see how humanity learned to choreograph this invisible ballet, to make electrons march to our tune, lighting our nights and powering our dreams. Long before anyone understood what electricity was, people knew it existed. They felt it in the prickling air before a storm, saw it split the sky in brilliant, terrifying forks, and if they were very unlucky, experienced its power firsthand. Lightning was electricity's calling card, its dramatic announcement that something powerful and mysterious moved through the world. For most of human history, this force was firmly in the realm of the gods. Zeus hurling thunderbolts, Thor wielding his hammer, divine anger made visible and devastating. But humanity has always been curious about things that might kill us. It's a peculiar trait of our species. We see something dangerous and mysterious, and instead of just avoiding it like sensible creatures, we think, I wonder how that works. This curiosity would eventually tame lightning itself, but the journey there was long, winding, and occasionally hair-raising in the most literal sense. The ancient Egyptians, those careful observers of the natural world, knew about electric fish. The Nile held electric catfish that could deliver shocks strong enough to stun prey or discourage predators. They called these fish the thunderers of the Nile, which shows they recognized some connection between the fish's shock and the lightning in the sky. The ancient Romans went a step further. They actually tried using electric rays as a medical treatment. Got a headache? Stand on an electric ray. Gout giving you trouble? Electric ray. It probably didn't cure much, but it certainly gave patients something else to think about. But the real story of electrical discovery begins in the age of wigs, waistcoats, and wondering. The 1600s saw the birth of what we might recognize as the scientific method, and with it came systematic investigations into electricity's nature. Enter William Gilbert, physician to Queen Elizabeth I and a man with an unusually intense interest in magnets and amber. Gilbert was the first to use the word electricus to describe the force that made rubbed amber attract small objects. He spent years rubbing various materials with cloth, fur and silk, carefully noting which ones developed this attractive power. It must have been quite a sight, one of England's most respected physicians, spending his days vigorously rubbing gems and minerals like some sort of scholarly shoeshiner. But his systematic approach paid off. He discovered that many materials could be electrified through friction, not just amber. Glass, sulfur, sealing wax. The list grew with each experiment. What Gilbert didn't know was that he was documenting which materials easily gave up or accepted electrons. But even without understanding the mechanism, he laid the groundwork for everything that followed. Science, after all, often involves carefully describing what happens long before anyone understands why. The 1700s brought electricity into the realm of parlour entertainment. Static electricity machines, essentially mechanized versions of rubbing amber with fur, became popular among the wealthy and curious. These contraptions used rotating glass spheres or cylinders that rubbed against leather pads, building up impressive charges. Demonstrators would create sparks, make people's hair stand on end, and even create human chains where a shock would pass from person to person. It was science as spectacle, and audiences loved it. One such demonstration changed the course of history. In 1746, Peter van Musschenbroek, working in the Dutch city of Leiden, was trying to store electrical charge in a glass jar filled with water. Through a series of accidents, the best kind of scientific discovery, he created what became known as the Leyden jar, the first capacitor, a device that could store significant amounts of electrical charge and release it all at once. The shock it delivered was powerful enough to knock grown men off their feet. Van Musschenbroek himself reported that he thought he was dying when he first experienced it, and recommended that no one else try the experiment. Naturally, everyone immediately wanted to try it. News of the Leyden jar spread across Europe like, well, electricity. Soon, investigators everywhere were building bigger jars, connecting them in series, and seeing just how large a shock they could create. It was dangerous, thrilling, and utterly captivating. For the first time, humans could bottle lightning, or at least something that seemed very much like it, which brings us to perhaps the most famous electrical experimenter of them all, Benjamin Franklin. Now, Franklin was many things: printer, diplomat, inventor of bifocals, and dispenser of pithy wisdom. But he was also genuinely brilliant when it came to electricity. In the 1740s and 50s, he performed a series of experiments that transformed electrical study from a collection of curious phenomena into something approaching a science. Franklin proposed that electricity was not created by friction, but was instead a fluid that existed in all matter. Rubbing materials together didn't create electricity, it just moved this fluid from one object to another. He introduced the terms positive and negative to describe the two states, positive having an excess of this fluid, negative having a deficit. We now know his fluid model wasn't quite right, it's electrons that move, not a fluid, but his terminology stuck. Every battery in your house has plus and symbols that trace back to Franklin's guess about electrical fluid. But Franklin's most famous experiment was also his most dangerous. In 1752, he flew a kite in a thunderstorm. Let's pause for a moment to appreciate how spectacularly bad an idea this was. Franklin was essentially trying to create a lightning rod with himself at the bottom. The fact that he survived was more luck than judgment. Other experimenters trying to replicate his work were killed. What Franklin was trying to prove was that lightning and laboratory electricity were the same thing. He attached a metal key to the kite string and, as the story goes, when lightning struck, he was able to draw sparks from the key, charge a Leyden jar, and perform all the same tricks that worked with friction-generated electricity. Lightning, it turned out, wasn't the province of gods after all. It was the same force you could create by rubbing a glass rod with silk, just on a much grander scale. This revelation led directly to one of Franklin's most practical inventions, the lightning rod. If lightning was just electricity looking for the easiest path to the ground, then why not give it one that didn't go through your house? Simple metal rods connected to the ground could protect buildings from lightning strikes. It was humanity's first real defense against one of nature's most dramatic displays, and it worked beautifully. The late 1700s and early 1800s saw electricity move from novelty to serious study. Luigi Galvani, an Italian physician, discovered that dead frogs' legs would twitch when touched with different metals. He thought he'd discovered animal electricity, a life force that animated living things. His nephew, Giovanni Aldini, took this idea to spectacular extremes, using electricity to make executed criminals' bodies move in front of horrified and fascinated audiences. It was macabre theatre, but it planted the seed of an idea that would later bloom in Mary Shelley's Frankenstein. Galvani's rival, Alessandro Volta, had a different interpretation. He believed the electricity came not from the frog but from the contact between different metals. To prove his point, he built the first true battery in 1800, a stack of alternating copper and zinc discs separated by cloth soaked in salt water. This voltaic pile could produce a steady flow of electricity, not just the brief sparks of static machines or Leyden jars. For the first time, experimenters had a reliable, controllable source of electrical current. The battery changed everything. Now scientists could study electricity's effects systematically. They could run current through wires, solutions, and gases. They could measure, compare, and begin to understand. Within decades, this understanding would transform from laboratory curiosity to world-changing technology. The 1800s became the century of electrical innovation. Michael Faraday discovered that moving a magnet near a wire could generate electricity, the principle behind every electrical generator. Samuel Morse developed the telegraph, turning electrical pulses into long-distance communication. By the 1870s and 80s, electric lights began to appear, promising to turn night into day at the flip of a switch. Which brings us to one of history's most famous technological feuds, the war of currents between Thomas Edison and Nikola Tesla, backed by George Westinghouse. Edison, the celebrated inventor of the phonograph and the practical incandescent light bulb, championed direct current DC electricity. Tesla, the brilliant and eccentric Serbian engineer, advocated for alternating current AC. The battle was fierce and sometimes ugly. Edison went so far as to publicly electrocute animals with AC power to demonstrate its danger, coining the term Westinghoused for being electrocuted. He even helped develop the electric chair as a further demonstration of AC's deadliness. It was a public relations war fought with voltage and fear. But Tesla and Westinghouse had physics on their side. AC could be easily transformed to different voltages, allowing electricity to be transmitted over long distances at high voltage, reducing losses, then stepped down for safe use in homes. DC couldn't do this effectively with the technology of the time. When Westinghouse won the contract to light the 1893 World's Fair in Chicago with AC power, the war was essentially over. The fair's 100,000 incandescent lights, powered by Tesla's polyphase system, showed the world the future of electricity. By the end of the 19th century, electricity had transformed from a mysterious force that split the sky to a servant of humanity. Power plants began to dot the landscape. Cities strung webs of copper wire. The night began its long retreat before the advance of electric light. In less than 150 years, we'd gone from rubbing amber with fur to illuminating entire cities with the flow of electrons. But this was just the beginning. Understanding how to generate and use electricity was one thing. Understanding what it actually was, that would require peering into the atom itself, into a quantum world stranger than any Victorian scientist could have imagined. The discovery of electricity's true nature would revolutionize not just technology, but our entire understanding of reality itself. If you could shrink yourself down, and I mean really shrink, past the size of a grain of sand, past the width of a human hair, past even the tiniest bacterium, you'd eventually reach a scale where the familiar rules of our world begin to dissolve into something far stranger. Welcome to the inside of an atom, where particles dance to quantum rhythms and electricity reveals its true nature. For most of human history, atoms were just an idea, a philosophical notion that matter might be made of indivisible particles. The word itself comes from the Greek atomos, meaning uncuttable. But atoms, as we discovered in the early 20th century, are anything but indivisible. They're more like miniature solar systems, if solar systems followed the bizarre laws of quantum mechanics, rather than the orderly paths of planets. At the heart of every atom sits the nucleus, a tight cluster of protons and neutrons. The protons carry positive charge. They're the optimists of the particle world, electrically speaking. Neutrons, true to their name, are neutral, carrying no charge at all. They're the peacekeepers, helping to hold the nucleus together despite the fact that all those positive protons should be frantically trying to fly apart. If the atom were the size of a cathedral, the nucleus would be no bigger than a housefly buzzing about in the centre. All that space, all that emptiness, and yet atoms feel solid to us. It's one of nature's most elegant illusions, but we're here for the electrons, those restless sprites that give electricity its character. Electrons don't orbit the nucleus like planets around the sun, despite what those tidy diagrams in textbooks might suggest. Instead, they exist in probability clouds, regions where they might be found if you looked. It's as if each electron is playing an endless game of quantum hide-and-seek, and the best we can do is map out their favourite hiding spots. These hiding spots, called orbitals, come in various shapes: spheres, dumbbells, flowers with 4 petals. The electrons fill them up according to strict rules, like apartment buildings where certain floors must be occupied before others can be. The electrons in the innermost orbitals closest to the nucleus are the home bodies. They're deeply attached to their atom, bound by the strong positive pull of the protons. But the electrons in the outermost orbitals, the ones farthest from the nucleus's influence, these are the social butterflies, the ones that make electricity possible. Why can't electrons sit still? It's not that they're fidgety by nature, well, maybe a little. It's that at the quantum scale, the very concepts of sitting still and being in one place become meaningless. The Heisenberg uncertainty principle, and doesn't that sound like something you'd blame when you lose your keys, tells us that we can never know both an electron's exact position and its exact momentum at the same time. The more precisely we pin down where it is, the less we know about where it's going. It's not just that we can't measure both, it's that both don't exist simultaneously in any definite way. An electron at rest is a contradiction in terms, like a wave that doesn't wave or a dance that doesn't move. This quantum restlessness is what makes chemistry possible, and chemistry is what makes electricity flow. You see, atoms are rather particular about their electron arrangements. They have preferred configurations, usually involving full outer orbitals. Atoms will share, steal, or donate electrons to achieve these perfect arrangements, and it's this constant negotiation that creates the electrical properties of different materials. Take copper, that champion conductor. A copper atom has 29 electrons arranged in their quantum layers, with just one lonely electron in its outermost orbital. This electron is barely holding on, like someone gripping the outer edge of a merry-go-round. Give it the slightest encouragement, a voltage, say, and off it goes, hopping to the next atom, which sends its own outer electron hopping along, and so on. This cascade of electron musical chairs is what we call electrical current. Now consider rubber. Its atoms hold their outer electrons in a tight embrace, all orbitals satisfactorily filled. Thank you very much. These electrons would need enormous encouragement to leave home. Push them with normal voltages and they simply refuse to budge. This is what makes rubber such a good insulator. Its electrons are committed homebodies. But here's where things get wonderfully weird. Between the conductors and the insulators lies a special class of materials that changed our world: semiconductors. Silicon, the stuff of computer chips and solar panels, is the most famous. Pure silicon is actually a rather poor conductor. Its electrons are reasonably content where they are, but add just a tiny impurity, a few atoms of phosphorus here, some boron there, and suddenly you can control its electrical behavior with exquisite precision. This process, called doping, which has nothing to do with athletics or scandals, is like social engineering at the atomic scale. Add phosphorus, which has an extra electron to spare, and you create N-type silicon with mobile negative charges. Add boron, which has one fewer electron than silicon wants, and you create P-type silicon with holes, spots where an electron should be but isn't. These holes act like positive charges, and electrons can hop from atom to fill them, making the holes appear to move in the opposite direction. It's like watching a gap in traffic flow backward as cars move forward to fill it. Put N-type and P-type silicon together and magic happens. Electrons can flow easily one way but not the other. You've created a diode, an electrical one-way valve. Arrange them more cleverly and you get transistors, the switches that can turn current on and off billions of times per second. Every computer, every smartphone, every digital device is essentially a crystal of carefully contaminated silicon channeling electrons through microscopic mazes of atomic precision. The speed of electricity versus the speed of electrons is one of those delightful paradoxes that shows how our intuitions can lead us astray. When you flip a light switch, the electrical signal travels through the wire at roughly 2/3 the speed of light. The bulb illuminates almost instantly, even if it's far away. But the individual electrons, they're drifting along at about the speed of a lazy snail, perhaps a few millimeters per second. How can this be? Think of a long pipe filled with marbles. Push a marble in one end, and a marble pops out the other end almost immediately. You don't have to wait for your specific marble to travel the whole length. The push itself propagates through all the marbles at the speed of sound in marble. Similarly, in a wire, the electric field propagates at enormous speed, pushing all the electrons along together. Each electron only needs to nudge its neighbour a tiny bit, and this nudge races through the wire far faster than any individual electron moves. This is why alternating current is so clever. The electrons don't actually need to go anywhere in particular. They just wiggle back and forth in place like dancers doing the twist. In the AC power from your wall outlet, electrons oscillate back and forth 60 times per second, 50 in some countries, never actually travelling more than a fraction of a millimetre. Yet this coordinated wiggling carries energy from power plants to your home, like a stadium wave that circles the stands, while each person just stands up and sits down in place. The quantum behaviour of electrons gets even stranger when we cool things down. At very low temperatures, in certain materials, something remarkable happens. Electrical resistance disappears entirely. This phenomenon, called superconductivity, occurs when electrons pair up and move through the material in perfect synchronization, like dancers in an elaborate ballet where no one ever steps on anyone else's toes. The paired electrons flow without losing any energy to resistance, creating a current that could, in principle, flow forever. We use superconductors in MRI machines, particle accelerators, and experimental quantum computers. There's ongoing research into materials that could superconduct at higher temperatures, perhaps even room temperature. Imagine power lines that lose no energy to resistance, or computers that generate no heat. The electron's quantum dance might one day transform our technology yet again, but even in ordinary materials at room temperature, the behaviour of electrons is profoundly quantum. They tunnel through barriers that should be impenetrable, like ghosts walking through walls. They interfere with themselves, creating patterns of probability like waves on water. They exist in superposition, being in multiple states at once until we measure them and force them to choose. This atomic ballet, this endless quantum choreography, is happening right now in every wire in your walls, every circuit in your devices, every atom in your body. Trillions upon trillions of electrons, following the strange rules of the quantum realm, create the macroscopic phenomenon we call electricity. It's a dance that never stops, never slows, never misses a beat. And we've learned to conduct this orchestra, to guide these quantum dancers through our circuits and machines. From the simple flow of current through a wire to the complex cascades of computation in a microprocessor, we're manipulating matter at its most fundamental level. Every time you turn on a light or send a text message, you're choreographing the movement of countless electrons, directing a performance that spans from the quantum to the cosmic. Picture, if you will, a river. Not just any river, but one that flows uphill when it needs to, splits into countless tributaries that somehow all know exactly where to go, and can reverse direction 60 times every second. Oh, and it's invisible. This impossible river flows through nearly every wall of your home, and you summon it forth with the casual flick of a switch. We call it electric current, and it's one of humanity's most elegant acts of control over the natural world. Current comes in two main flavours, like ice cream, if ice cream could power your refrigerator. There's direct current, DC, where electrons flow steadily in one direction like a well-mannered queue. And there's alternating current, AC, where electrons shimmy back and forth like dancers doing the electric slide. Both have their place in our electrical ecosystem, and the story of how we ended up with both is a tale of innovation, stubbornness, and the occasional electrocuted elephant, though we touched on that unfortunate bit already. Direct current is the simpler of the two, conceptually speaking. Electrons flow from negative to positive, like water flowing downhill. Batteries produce DC. The electrons march out of the negative terminal through your circuit and back to the positive terminal in an orderly procession. It's straightforward, reliable, and it's what most of our electronic devices actually want. Your phone, laptop, LED lights, they're all DC creatures at heart. So why, you might wonder, does the power coming from your wall outlet wiggle back and forth in alternating current? Why make things complicated? The answer lies in a bit of electromagnetic cleverness and the stubborn realities of physics. You see, when you need to send power over long distances, say from a hydroelectric dam to a city, you face a problem. Electrical current flowing through a wire encounters resistance, and resistance means energy lost as heat. It's like trying to push honey through a straw. Some of your effort goes into warming up the honey rather than moving it along. The amount of power lost is proportional to the square of the current, which is a fancy way of saying that doubling the current quadruples your losses. Not ideal when you're trying to light up a city 100 miles away. The solution? Send the power at very high voltage and low current. Think of it like this. You can deliver the same amount of water per minute through a pipe either by pushing a lot of water slowly or a little water very fast. High voltage is the electrical equivalent of high pressure. Less current needs to flow to deliver the same power. But here's the catch. High voltage is spectacularly dangerous. You can't have 100,000 volts coming out of your wall socket unless you want your toast to be very, very crispy indeed. This is where AC shows its party trick. Thanks to the principles of electromagnetic induction discovered by Faraday, AC voltage can be easily transformed up or down using, appropriately enough, transformers. These devices, which hide in those grey boxes on power poles and in the humming cabinets outside buildings, use the magic of magnetism to change voltages. Send AC through a coil of wire, and it creates a changing magnetic field. Put another coil nearby, and that changing field induces a voltage in the second coil. Make the second coil have more turns than the first, and voila, higher voltage. Fewer turns, lower voltage. It's like an electromagnetic gear system for electricity. DC, at least with the technology available in Edison's time, couldn't do this voltage-changing trick easily. That's why, despite Edison's dramatic demonstrations of AC's dangers, Tesla and Westinghouse won the war of currents. AC could travel long distances at high voltage, then be stepped down to safe levels for home use. The whole power grid became possible because of this alternating wiggle. Speaking of the grid, let's follow the journey of electricity from a power plant to your bedside lamp. It's quite the adventure, involving multiple voltage changes, switching stations, and a level of coordination that would make air traffic control jealous. It starts at a power plant, where something, falling water, steam from burning coal or gas, wind, nuclear fission spins a turbine. This turbine is connected to a generator, which is essentially a giant magnet spinning inside coils of wire. Remember Faraday's discovery? Moving magnets near wires creates electrical current. The generator produces AC electricity, typically at around 20,000 volts. But 20,000 volts won't get your electricity very far without substantial losses. So the first stop is a step-up transformer at the power plant, which boosts the voltage to anywhere from 115,000 to 765,000 volts for long-distance transmission. These high-voltage lines are the ones you see marching across the countryside on tall metal towers, keeping their dangerous energy well away from trees, buildings, and curious humans. The electricity zooms along these transmission lines at nearly the speed of light. Remember, it's the electrical field moving fast, not the individual electrons. When it nears its destination, it enters a substation, where step-down transformers reduce the voltage to something more manageable, perhaps 13,000 volts for distribution around a neighbourhood. From there, it travels along smaller distribution lines, the ones you typically see running along residential streets. Just before entering your home, it makes one final stop at another transformer, that cylinder you see on power poles, or that green box in someone's front yard. This brings the voltage down to the 120 or 240 volts, depending on your country, that your home uses. Finally, it flows through your home's wiring to outlets and switches, ready to power anything you plug in. The entire journey from power plant to your lamp might cover hundreds of miles and involve a dozen voltage changes, yet it happens continuously, reliably, billions of times per second across millions of homes. But here's something that might surprise you. All the AC electricity in a large power grid is synchronized. Every generator feeding into the grid is spinning in perfect lockstep, like a vast electromagnetic ballet performed across entire continents. In North America, they all complete exactly 60 cycles per second. In Europe and most of the world, it's 50 cycles per second. This synchronization is crucial. If one generator were out of sync, it would be like trying to push a revolving door the wrong way. The results would be dramatic. This is why power grids are both remarkably robust and surprisingly fragile. They can route around damage, share loads, and keep running even when parts fail. But they also require precise balance between generation and consumption. Use more power than is being generated, and the frequency drops. Generate more than is being used, and it rises. Grid operators constantly adjust power generation to match demand, turning power plants on and off, storing excess energy, and sometimes even asking large users to reduce consumption during peak times. Why does your wall outlet hum? That's the sound of alternating current at work. As current flows back and forth through wires and transformers, it creates changing magnetic fields. These fields can make metal parts vibrate slightly at the frequency of the AC, 60 times per second in North America. It's usually quiet, but in transformers with loose parts or under heavy load, this vibration becomes audible as that characteristic electrical hum. It's the sound of electrons dancing to a very precise beat. Inside your home, your electrical system is like a tree. The main trunk comes in through your electrical panel, that box with all the circuit breakers or fuses. From there, branches split off to different parts of your house. Each branch is a circuit protected by its own breaker that will cut the power if too much current flows. It's a safety system born from hard experience. Before circuit breakers, electrical fires from overloaded wires were distressingly common. The outlets in your walls are cleverly designed too. In many countries they're polarized. One slot is slightly larger than the other. This ensures that the hot wire, the one that actually carries the varying voltage, and the neutral wire, the return path, are always connected the same way. The third hole in many outlets is for grounding, a safety path that gives electricity a route to the earth if something goes wrong, protecting you from becoming that path yourself. When you plug something in, you're completing a circuit. Electrons flow from the hot wire through your device, doing whatever work you've asked of them, lighting a bulb, spinning a motor, heating an element, and back through the neutral wire. It's a closed loop, and it has to be. Electrons can't just pile up somewhere. What goes out must come back. Break the loop anywhere, and the flow stops. This is how switches work. They're just controlled breaks in the circuit, like drawbridges for electrons. The transformer deserves a moment of appreciation, for it truly is one of the most elegant devices humans have created. No moving parts, no batteries, no complicated electronics, just coils of wire and a core of iron. Yet this simple arrangement can step voltages up or down with remarkable efficiency, typically losing only 1% or 2% of the energy passing through. Inside a transformer, the primary coil creates a magnetic field that expands and collapses with the alternating current. This changing field passes through the iron core and into the secondary coil, where it induces a voltage. The ratio of turns between the coils determines the voltage change. It's electromagnetic poetry, energy dancing from electrical to magnetic and back to electrical again, changing its costume along the way. Those power adapters cluttering your drawers? Many of them contain tiny transformers, stepping your wall voltage down to the 5 or 12 volts your devices need. Though increasingly, these bulky transformers are being replaced by switching power supplies, clever circuits that chop the AC into high-frequency pulses, transform them through much smaller transformers, then smooth them back into steady DC. It's why phone chargers have gotten so much smaller over the years. Higher frequencies allow for tinier transformers. Motors and generators are transformers' cousins in the electromagnetic family. A generator turns motion into electricity. A motor turns electricity into motion. In fact, they're so similar that the same device can often do both jobs. Those electric cars silently gliding past. When they brake, their motors become generators, turning the car's momentum back into electricity to charge the battery. It's called regenerative braking, and it's like running our river metaphor in reverse, using the flow to pump water back uphill. The global power grid is one of humanity's largest machines, arguably the largest. It spans continents, crosses oceans via underwater cables, and coordinates the output of thousands of power plants to meet the constantly changing demands of billions of users. It's a machine so vast that it has its own weather patterns, electrical storms that have nothing to do with clouds, but rather with the surges and flows of power across transmission lines. This grid is evolving too. Where once electricity flowed one way, from big power plants to users, now it's becoming bidirectional. Solar panels on rooftops feed power back into the grid. Electric cars could someday act as mobile batteries, storing excess power and releasing it when needed. The dumb grid is becoming smart, with sensors and computers managing flow in real time, predicting demand, and routing around problems. But let's return to your bedside lamp, where this whole journey ends. When you flip that switch, you're commanding electrons across hundreds of miles of wire. A power plant somewhere responds to the infinitesimal increase in demand. Generators spin a tiny bit harder, transformers hum a microscopic note higher, and in less time than it takes to blink, light fills your room. It's mundane and miraculous all at once. We've built a river of electrons that flows through our walls, always ready, always waiting. We've tamed lightning and made it obedient to our smallest gesture. AC and DC, transformers and transmission lines, circuit breakers and outlets. It's all part of an intricate dance that brings energy from distant places to the exact spot where we need it, at the exact moment we need it. And it all works so well that most of the time, we don't even think about it. We flip switches and plug things in with the same casual confidence our ancestors had in the sunrise. The invisible river flows on command, and we've become so accustomed to its presence that its absence, a power outage, feels like a violation of natural law. But perhaps that's the greatest triumph of our electrical age. We've made the miraculous feel mundane. We've turned the cosmic forces that split atoms and spin galaxies into something as everyday as making toast. The electrons dance on, AC and DC, wiggling and flowing through their copper highways, and we conduct this vast orchestra with nothing more than the flip of a switch. How extraordinarily ordinary it's all become. If electricity were a person at a party, magnetism would be its inseparable dance partner. They move together so perfectly, respond to each other so intimately, that for most of human history we thought they were two completely different phenomena. Surprise, they're actually the same force wearing different costumes, and discovering this connection revolutionized our understanding of the universe. Let's start with magnetism itself, that invisible force that makes compass needles point north and holds your shopping list to the refrigerator. Like electricity, magnetism was noticed long before it was understood. The ancient Chinese were using magnetic compasses for navigation over 2,000 years ago. The Greeks knew about lodestones, naturally magnetic rocks that could attract iron. The word magnet itself comes from Magnesia, a region in Greece where these mysterious stones were found. But here's the delightful thing. Every time an electron moves, it creates a magnetic field, and every time a magnetic field changes, it pushes on electrons. Electricity and magnetism are locked in an eternal dance, each one creating the other, like partners who take turns leading. This cosmic tango is what makes possible everything from electric motors to radio waves to the light entering your eyes right now. The connection between electricity and magnetism remained hidden until 1820, when Hans Christian Ørsted, a Danish physicist, made a discovery that probably made him drop his coffee. He was demonstrating electrical current to students when he noticed that a compass needle near his wire deflected whenever current flowed. The electrical current was creating a magnetic field. This was like discovering that your cat had been secretly writing poetry all along. Two things you thought were completely separate turned out to be intimately connected. News of Ørsted's discovery spread through the scientific community like, well, electricity. Within months, André-Marie Ampère in France had worked out the mathematical relationship between current and magnetic fields. If you run current through a straight wire, the magnetic field forms concentric circles around it, like ripples around a stick poked in water. Coil the wire into a spiral, and the magnetic fields add up to create what's essentially an electromagnet. A magnet you can turn on and off with a switch. But the real electromagnetic revolution came from Michael Faraday, a British scientist with no formal mathematical training, but an intuition for physics that bordered on the supernatural. In 1831, Faraday wondered, if electricity could create magnetism, could magnetism create electricity? His experiments were elegantly simple. He wrapped 2 coils of wire around an iron ring completely separate from each other. When he connected one coil to a battery, he expected to see continuous current in the second coil. Instead, he saw something far more interesting. The second coil showed current only at the moment he connected or disconnected the battery. It wasn't the magnetic field itself that created electricity, but the change in the magnetic field. This principle, electromagnetic induction, is the foundation of our electrical age. Move a magnet near a wire and you create current. Move a wire near a magnet, same thing. It doesn't matter which moves, it's the relative motion that counts. This is how every electrical generator works, from massive power plant turbines to the tiny dynamo that powers your bicycle light. Spin magnets near coils of wire, or spin coils near magnets, and you've got electricity. Faraday also gave us a beautiful way to visualize these invisible forces. He imagined lines of force extending from magnets and around current-carrying wires. Sprinkle iron filings near a magnet, and they align themselves along these lines, making the invisible visible. These field lines aren't just useful metaphors, they represent something real about how magnetic forces extend through space, like invisible threads connecting everything that feels the force. The electromagnetic tango reaches its full expression in generators and motors, those workhorses of our electrical civilization. A generator is simply a device that moves magnets and coils relative to each other, converting mechanical motion into electrical current. The motion can come from anywhere: steam turbines, water wheels, wind turbines, even hand cranks. As long as something's moving, Faraday's induction can transform that motion into electricity. Here's the beautiful part. Motors are just generators running backward. Send electrical current through a coil in a magnetic field, and the coil experiences a force. Arrange things cleverly, and this force creates rotation. The same device that generates electricity when you spin it will spin when you send electricity through it. It is like a reversible jacket for energy conversion. Inside an electric motor, electromagnets switch on and off in sequence, creating a rotating magnetic field that drags the motor's rotor around like an invisible hand. The timing has to be perfect. Each electromagnet must switch at just the right moment to keep pulling the rotor forward. In old-fashioned motors, this timing was handled by brushes, sliding electrical contacts that mechanically switch the current. Modern motors often use electronic switching, which is more efficient and doesn't wear out. But why do magnets stick to refrigerators and not to you? Or to aluminum, for that matter? The answer lies in how different materials respond to magnetic fields. Iron and its magnetic cousins, nickel, cobalt, and some rare earth elements, are ferromagnetic. Their atoms act like tiny magnets, and they tend to align with each other in regions called domains. Normally, these domains point in random directions, cancelling out. But expose iron to a magnetic field, and the domains line up, turning the whole piece into a magnet. Most materials, including you, are diamagnetic or paramagnetic. Fancy words meaning they respond weakly to magnetic fields. Water is slightly diamagnetic, which is why you can levitate a frog with a strong enough magnet. The frog is mostly water. Yes, this has been done. No, the frog didn't enjoy it. But the effect is so weak that you'd need incredibly powerful magnets to notice it in everyday life. Permanent magnets, like those on your fridge, are ferromagnetic materials whose domains have been locked in alignment. Hit them hard enough or heat them enough and the domains randomize again, destroying the magnetism. This temperature limit, called the Curie point, is why magnets lose their strength in fires. It's also why the Earth's core, despite being mostly iron, isn't a permanent magnet. It's far too hot. The electromagnetic connection goes even deeper than motors and generators. In the 1860s, James Clerk Maxwell, a Scottish physicist with an impressive beard and even more impressive mathematics, realised that electricity and magnetism were two faces of a single force. His equations, 4 beautiful mathematical statements, showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. More remarkably, Maxwell's equations predicted that these intertwined fields could break free from wires and magnets and propagate through space as waves. The speed of these electromagnetic waves, according to his calculations, exactly the speed of light. This wasn't a coincidence. Light is an electromagnetic wave, just one our eyes happen to detect. Radio waves, microwaves, X-rays, gamma rays. They're all the same phenomenon at different frequencies, all electricity and magnetism dancing together through space. Think about that for a moment. The same force that lights your lamp also carries your Wi-Fi signal, heats your food in the microwave, and brings you images from across the universe. When you tune a radio, you're using a circuit that resonates at a particular frequency, plucking one electromagnetic song out of the countless waves washing over you right now. Your phone is a marvel of electromagnetic engineering, sending and receiving waves that encode your voice, your texts, your endless scrolling, all through the interplay of electricity and magnetism. This electromagnetic radiation is created whenever charges accelerate. Jiggle an electron, and it sends out electromagnetic waves like ripples on a pond. The faster the jiggling, the higher the frequency of the waves. Radio transmitters are basically electron jigglers, shaking charges back and forth millions or billions of times per second. Your microwave oven jiggles electrons 2.45 billion times per second, creating waves just the right size to be absorbed by water molecules in your food. Even the warmth you feel from a fire is electromagnetic radiation, infrared waves created by the jiggling of charged particles in the hot gases and glowing embers. Your body emits infrared too, which is how thermal cameras can see you in the dark. You're literally glowing with electromagnetic radiation right now, just at frequencies your eyes can't detect. The dance between electricity and magnetism also explains why power lines can interfere with radios, why MRI machines need such powerful magnets, and why you shouldn't put your credit cards near strong magnets. The magnetic strip stores data using tiny magnetic domains that can be scrambled. It's why electric guitars work. The strings disturb the magnetic field of the pickups, creating electrical signals that become sound. It's why transformers hum and motors whir and generators generate. But perhaps the most profound aspect of electromagnetism is how it reveals the universe to be deeply interconnected. A moving charge here creates a field that extends, in principle, throughout all of space, weakening with distance but never quite reaching zero. Every electron in motion, every current in every wire, every broadcast from every radio tower adds its voice to the electromagnetic chorus of the universe. We swim in an ocean of oscillating fields, most too weak to notice, but all intertwining in an incredibly complex dance. And we've learned to choreograph this dance with extraordinary precision. We've built machines that can detect the magnetic field of a single electron, amplifiers that can boost the faintest electromagnetic whisper into thunderous sound, and transmitters that can send coherent electromagnetic waves to spacecraft billions of miles away. We've turned the electromagnetic tango into technology, and in doing so, we've woven it into the fabric of our daily lives. So the next time you use anything electrical, remember, you're not just pushing electrons around, you're conducting an electromagnetic symphony, where every moving charge creates magnetic fields, every changing field pushes on charges, and the two dance together in patterns of extraordinary complexity and beauty. It's a dance that's been going on since the universe began, and we've just recently learned to hear the music. The sky darkens to an ominous purple grey. The air feels thick, electric, like the whole world is holding its breath. Then, in an instant that seems to last forever, a jagged finger of pure light reaches down from the clouds, branching and rebranching like some celestial tree growing at the speed of, well, lightning. The thunder follows, a sound you feel as much as hear, rattling windows and setting off car alarms. For a brief moment, nature shows us electricity in its wildest, most untamed form. Lightning is electricity without the civilizing influence of wires and circuits. It's what happens when the patient accumulation of charge reaches a breaking point and decides to take the shortest path home, even if that path happens to be through several miles of air that really doesn't want to conduct electricity. It's nature's own electrical spectacular, and it happens about 100 times every second somewhere on Earth. But how does the sky become a battery? It starts with ice, wind, and a lot of vertical real estate. Inside a thundercloud, technically a cumulonimbus if you're feeling fancy, powerful updrafts carry water droplets high into the freezing upper atmosphere. These droplets freeze into ice crystals, which then begin a complex dance of collision and separation. Larger ice particles fall while smaller ones rise, and in their constant bumping and grinding, electrons get transferred. It's like shuffling across a carpet on a cosmic scale. The exact mechanism is still debated by scientists. Nature doesn't always reveal her secrets easily, but the result is clear. The top of the cloud becomes positively charged while the bottom becomes negative. The cloud has become a capacitor the size of a mountain, with voltage differences that would make power plant engineers weep with envy. As the charge builds, the electric field strength increases. Air is normally an excellent insulator, which is fortunate or we'd all be constantly electrocuted, but even air has its limits. When the electric field reaches about 3 million volts per meter, air begins to break down. Electrons get ripped from air molecules, creating a conducting channel of ionized gas called a plasma. This is the beginning of a lightning strike. But lightning doesn't simply blast from cloud to ground in one go. Instead, it sends out scouts. A nearly invisible channel of ionized air called a stepped leader zigzags downward from the cloud in steps of about 50 meters, each step taking about a microsecond. It's searching for the easiest path to ground, branching and rebranching like a river delta in fast forward. Meanwhile, as this invisible leader approaches the ground, the electric field at the surface intensifies dramatically. Sharp objects, trees, buildings, golf clubs held aloft by unfortunate players, experience even stronger fields. From these points, positive streamers reach upward, trying to meet the descending leader. It's an electrical romance with positive and negative charges reaching for each other across the gap. When a streamer finally connects with the stepped leader, usually when they're within a few dozen meters of each other, the circuit completes. Now comes the spectacular part. A massive current flows along the ionized channel, heating the air to about 30,000 Kelvin, 5 times hotter than the surface of the sun. This superheated air expands explosively, creating the shockwave we hear as thunder. The actual current flow in a lightning strike is mind-boggling. Peak currents can reach 30,000 amperes or more, though they last only milliseconds. For comparison, the current in your household wiring is typically 15 or 20 amperes. The total energy in a lightning bolt is actually not that enormous, about the same as a quarter ton of TNT, or what you'd use to power a 100-watt bulb for a few months. But it's the rate of energy delivery that's impressive, like drinking a year's worth of coffee in a millisecond. Lightning doesn't always strike the ground. In fact, most lightning never leaves the cloud. Intra-cloud lightning, sheet lightning, cloud-to-cloud lightning. The sky offers many paths for electrical discharge. There's even upward lightning, where the strike initiates from tall objects and travels up to the clouds. Skyscrapers and communication towers experience this regularly, which is why they're festooned with lightning rods and grounding systems. But Earth's atmosphere doesn't have a monopoly on electrical dramatics. Jupiter's storms produce lightning bolts that would dwarf Earth's most impressive displays. Saturn, too, has lightning, detected by the radio waves it produces. Even Venus, with its hellish atmosphere, shows signs of electrical activity. It seems that wherever you have atmospheres and energy, nature finds a way to create its own light shows. Speaking of nature's electrical creativity, let's dive underwater to meet some of Earth's most shocking creatures. Electric fish have turned biological electricity into a superpower, using specially evolved cells to generate voltages that would be illegal in most household appliances. The electric eel, despite its name, it's actually a type of knife fish, is the heavyweight champion of bioelectricity. Large specimens can generate discharges of up to 600 volts, enough to stun a horse or light up a Christmas tree, as demonstrators occasionally show. They achieve this through thousands of specialized cells called electrocytes, stacked like batteries in series along much of their body length. Each electrocyte works on the same principle as your nerve cells, but optimized for maximum voltage. When triggered, ion channels open, allowing sodium to rush in and potassium to rush out, creating a voltage difference across the cell membrane. One cell might generate only about 150 millivolts, but stack 4,000 of them in series and you've got yourself a living stun gun. Electric eels use their power for navigation and communication as much as for hunting. They emit weak pulses constantly, creating an electric field around their body. Objects in the water distort this field, and the eel can sense these distortions with special receptors. It's like having radar that works in murky Amazonian rivers where eyes are nearly useless. When hunting, they can ramp up the frequency of pulses to electrically shout at hidden prey, forcing their muscles to twitch and reveal their location. Once found, a high-voltage discharge stuns the prey for easy consumption. Electric rays, found in oceans worldwide, use a different arrangement. Their electric organs are modified muscle tissue arranged in kidney-shaped formations on either side of their head. Large torpedo rays can generate up to 220 volts, not as impressive as an electric eel, but still enough to knock a human off their feet. They use this primarily for defense and to stun prey, lying buried in sand until an unsuspecting fish swims overhead. But here's what's truly remarkable. These electric fish can control their discharges with incredible precision. They can vary the voltage, frequency, and duration of their electrical output like living synthesizers. Some species of weakly electric fish in Africa and South America use complex electrical songs for communication and courtship. Males and females exchange electrical pulses in patterns that would make a telegraph operator jealous. The story of bioelectricity doesn't stop with fish that can shock you. Every living cell is, in a sense, electrical. Your neurons are firing electrical impulses as you read this. Your heart beats because of precisely timed waves of electrical activity. Even plants use electrical signals to communicate between roots and leaves. Life itself is an electrical phenomenon. Your brain is perhaps the most sophisticated electrical device on the planet. With about 86 billion neurons, each connecting to thousands of others, it's a network of unimaginable complexity. Each neuron is like a tiny battery, maintaining a voltage difference across its membrane. When stimulated, ion channels open in a cascade that sends an electrical pulse racing down the axon at speeds up to 120 meters per second. These electrical pulses, called action potentials, are your thoughts in motion. Every memory recalled, every decision made, every sensation felt is encoded in patterns of electrical activity. An EEG, electroencephalogram, can detect these patterns from outside your skull, revealing the electrical storms of thought. Different brain states, waking, sleeping, dreaming, have characteristic electrical signatures. Your brain even generates enough electrical activity to power a dim LED bulb, though extracting that power would be rather counterproductive. Your heart, too, is an electrical marvel. Specialized pacemaker cells generate regular electrical impulses that spread through the cardiac muscle, coordinating its contractions. An ECG, electrocardiogram, reads these electrical patterns, with each heartbeat producing a characteristic waveform, the P wave as the atria contract, the QRS complex as the ventricles fire, the T wave as they reset. It's an electrical signature as unique as a fingerprint. When this electrical system goes wrong, the results can be serious. Atrial fibrillation, where the upper chambers quiver chaotically instead of beating properly, is an electrical problem. So is ventricular fibrillation, where the main pumping chambers lose coordination. Defibrillators work by sending a strong electrical shock through the heart, essentially hitting the reset button on its electrical system and hopefully restoring normal rhythm. Even your muscles are electrically activated. When you decide to move, electrical signals race from your brain down your spinal cord and out to motor neurons. These neurons release chemicals at the muscle junction that trigger electrical changes in the muscle fibers, causing them to contract. An EMG, electromyogram, can detect this electrical activity, which is why physical therapists sometimes use electrical stimulation to activate muscles in injured patients. They're bypassing the normal control system and directly triggering the electrical response. The electrical nature of life goes deeper still. Cells maintain electrical gradients across their membranes, using them to power various cellular processes. Mitochondria, the powerhouses of the cell, use electrical gradients to produce ATP, the universal energy currency of life. Some bacteria can even conduct electricity through protein nanowires, creating living electrical circuits in sediments and biofilms. In fact, there's growing evidence that many biological processes we thought were purely chemical have electrical components. Wound healing appears to be guided partly by electrical fields. Some cancers have different electrical properties than healthy tissue. Bone growth responds to electrical stimulation. We're discovering that life is even more electrical than we imagined. This bioelectrical world extends beyond individual organisms. Some scientists propose that forests might use electrical signals transmitted through fungal networks to communicate between trees. Flowers generate electrical fields that bees can detect, helping them find nectar. The Earth itself maintains a global electrical circuit, with thunderstorms pumping charge into the ionosphere and fair weather regions providing the return path. So when you see lightning split the sky or an electric eel hunting in murky waters, you're witnessing the same fundamental force that animates your thoughts and drives your heartbeat. Electricity isn't just something we've harnessed for technology. It's woven into the very fabric of life. We are electrical beings living on an electrical planet under an electrical sky. The light show never really ends. Sometimes it's just too subtle for us to see. Welcome to the Quantum Cafe, where the rules of classical physics are politely but firmly left at the door. Here, in the realm of the very small, electricity reveals its true quantum nature, and things get delightfully weird. Particles exist in multiple states until observed. Electrons tunnel through barriers that should be impenetrable, and the very act of measurement changes what you're measuring. Pull up a chair, order a probabilistic coffee, it both is and isn't decaf until you drink it, and let's explore how quantum mechanics makes our electronic world possible. At the scale of atoms and electrons, the smooth, predictable behaviour of classical electricity gives way to something far stranger. Remember how we talked about electrons orbiting the nucleus? Well, at the quantum level, orbit is far too concrete a word. Electrons exist in probability clouds, regions where they might be found if you looked. It's not that we don't know where they are, it's that they genuinely don't have a definite position until measured. They're everywhere and nowhere, like a cat that's somehow in every room of the house simultaneously until you actually look for it. This quantum fuzziness might seem like a bug in the universe's operating system, but it's actually the feature that makes modern electronics possible. You see, classical physics would predict that electrons orbiting a nucleus should spiral inward. radiating energy until they crash into the nucleus. Atoms should collapse in a fraction of a second. The fact that you exist to read this means something prevents this atomic catastrophe, that something is quantum mechanics. Electrons can only exist in specific energy states, like a staircase where you can stand on the steps but not between them. They can jump between levels by absorbing or emitting specific amounts of energy, but they can't exist in the gaps. This quantization, the fact that energy comes in discrete packets rather than smooth variations, is what gives quantum mechanics its name and atoms their stability. But here's where it gets interesting for our electrical story. In individual atoms, these energy levels are sharp and distinct. But bring atoms together into a solid, and something magical happens. The energy levels blur and spread, forming bands. In conductors, these bands overlap in ways that let electrons flow freely. In insulators, there's a large gap between bands that electrons can't cross. And in semiconductors, the gap is just right. Not too big, not too small, but just perfect for manipulation. This is where human cleverness enters our quantum cafe. By carefully adding impurities to semiconductors, remember that process called doping? We can control exactly how electrons behave. Add a bit of phosphorus to silicon, and you get extra electrons lounging in the conduction band. Add boron instead, and you create holes, missing electrons that act like positive charges. It's like carefully seasoning a dish to get just the right flavour, except the flavour is electrical conductivity. The transistor, invented in 1947 at Bell Labs, was humanity's first great quantum mechanical device, though the inventors might not have fully appreciated the quantum nature at the time. A transistor is essentially a sandwich of different types of semiconductor that can switch electrical current on and off or amplify signals. But it works because of purely quantum mechanical effects. In a transistor, applying a small voltage to one terminal changes the quantum mechanical barriers that electrons face, allowing current to flow or blocking it. It's like having a quantum drawbridge that you can raise or lower with the tiniest effort. The first transistor was about the size of your palm. Today we pack billions of them onto chips smaller than your fingernail, each one switching billions of times per second. But transistors are just the beginning of our quantum electrical toolkit. Consider the LED, light-emitting diode, that probably illuminates your screen right now. When electrons in an LED fall from a higher energy band to a lower one, they emit photons. The colour of the light depends on the size of the energy gap, which we can engineer by choosing different semiconductor materials. Red LEDs came first because the energy gap for red light is smaller. Blue LEDs, requiring a larger gap, took decades longer to perfect and earned their inventors a Nobel Prize. The quantum world gets even stranger with a phenomenon called tunneling. In classical physics, if you don't have enough energy to get over a barrier, you're stuck. It's like trying to roll a ball over a hill. Without enough initial speed, it rolls back down. But in quantum mechanics, particles can sometimes appear on the other side of barriers they shouldn't be able to cross. They don't go over, under, or around. They just quantum mechanically appear on the other side, like a ghost walking through a wall. This isn't science fiction. It's happening in your computer right now. Flash memory, the kind in USB drives and solid-state drives, stores data by trapping electrons behind quantum barriers. To write data, we apply a voltage that allows electrons to tunnel through an insulator and become trapped. To erase, we reverse the process. The electrons shouldn't be able to cross that insulating barrier according to classical physics, but quantum tunneling makes it possible. Scanning tunneling microscopes use the same effect to image individual atoms. A sharp needle is brought so close to a surface that electrons can tunnel between them. By measuring this tunneling current as the needle scans across the surface, we can map out the locations of individual atoms. It's like reading Braille with electrons instead of fingertips, except the bumps are atoms and the scale is unimaginably small. But perhaps the most mind-bending quantum effect in electronics is superposition, the ability of quantum systems to exist in multiple states simultaneously. In a classical bit, you have either 0 or 1, on or off, But a quantum bit, a qubit, can be both 0 and 1 at the same time, at least until you measure it. It's like a coin that simultaneously heads and tails until you look at it. This leads us to quantum computers, machines that harness superposition and another quantum property called entanglement to perform certain calculations exponentially faster than classical computers. While your laptop processes information one bit at a time, a quantum computer can explore multiple solutions simultaneously. It's still early days. Quantum computers are finicky, requiring temperatures near absolute zero and isolation from any disturbance, but they represent the ultimate expression of quantum electronics. The quantum cafe serves up another specialty: superconductivity. Cool certain materials below a critical temperature and something remarkable happens. Electrical resistance disappears entirely. Not just reduces, vanishes. Current can flow forever without losing energy. It's as if friction ceased to exist for electrons. This happens because at low temperatures, electrons can form coordinated pairs called Cooper pairs. These pairs move through the crystal lattice like synchronized swimmers, never colliding with atoms or losing energy. It's a purely quantum mechanical effect. The pairs are held together by tiny distortions in the lattice, like two bowling balls rolling in the depression each creates on a mattress. We use superconductors in MRI machines, where they create incredibly strong magnetic fields without consuming power once started. Particle accelerators use them to steer subatomic particles at nearly the speed of light. There's ongoing research into high-temperature superconductors that work at more practical temperatures. Imagine power lines with no losses, computers with no heat generation, or levitating trains floating on magnetic fields. The quantum nature of electricity also explains why computer chips are reaching fundamental limits. As transistors shrink, quantum effects become unavoidable. Electrons start tunneling where they shouldn't, leaking current and generating errors. The discrete nature of electric charge becomes apparent. You can't have half an electron. We're approaching the end of the Moore's law not because we lack clever engineers, but because we're running into the quantum mechanical bedrock of reality. But every challenge is also an opportunity. Researchers are exploring new quantum materials with exotic properties. Topological insulators conduct electricity only on their surfaces while remaining insulating inside. Quantum dots, tiny crystals that confine electrons in all three dimensions, can be tuned to emit specific colors of light or act as single electron transistors. Spintronics aims to use not just the charge of electrons, but their quantum mechanical spin to encode information. Even photosynthesis, it turns out, involves quantum effects. Plants and some bacteria use quantum coherence to efficiently channel energy from absorbed light to reaction centers. The energy explores multiple paths simultaneously, finding the most efficient route. Nature figured out quantum computing billions of years before us, using it to convert sunshine into the energy that powers most life on Earth. Your smartphone is a quantum mechanical marvel. The processor uses field effect transistors that control electron flow through quantum barriers. The camera sensor converts photons to electrons using the photoelectric effect that earned Einstein his Nobel Prize. The touchscreen uses quantum tunneling to detect your finger's position. The whole device is a testament to our ability to understand and harness quantum mechanics. And yet, for all our quantum cleverness, the quantum cafe reminds us to stay humble. Quantum mechanics is fundamentally probabilistic. We can predict the likelihood of events, but not determine them with certainty. Einstein famously objected that God does not play dice, but decades of experiments confirm that at the quantum level, dice are indeed being rolled. We've learned to load these quantum dice to make the outcomes we want more probable, but we can't eliminate the fundamental uncertainty. So here we sit in the quantum cafe, surrounded by devices that work because of quantum mechanics, even as the theory challenges our everyday notions of reality. Electrons that are waves and particles, barriers that can be tunneled through, states that exist in superposition until observed. It's a strange menu, but it's the one the universe serves at the smallest scales. The next time you use any electronic device, remember that you're wielding quantum mechanics. Those orderly flows of current arise from quantum chaos, reliability from fundamental uncertainty, classical behavior from quantum rules. We've taken the weirdest, most counterintuitive theory in physics and used it to build the foundation of the modern world. Not bad for clever apes who evolved to understand throwing rocks and finding fruit, not quantum superposition and electron tunneling. You are electric, not metaphorically, not poetically, but literally, measurably, undeniably electric. Right now, as you read these words, billions of electrical impulses are racing through your neural networks. Your heart is beating to an electrical rhythm. Even the muscles holding you upright are contracting in response to electrical commands. You're a soft, warm, walking electrical storm, crackling with the same fundamental force that lights cities and powers stars. Let's start with your body's electrical system, beginning with those remarkable cells called neurons. Each one is like a living wire, capable of generating and transmitting electrical signals. But unlike the copper wires in your walls, neurons are selective about when and how they conduct electricity. They're more like very sophisticated switches that can decide whether a signal is important enough to pass along. A neuron at rest maintains an electrical potential across its membrane of about 70 millivolts. That might not sound like much. It's less than a tenth of what you get from a battery. But remember, this voltage exists across a membrane only about 7 nanometers thick. Scale that up, and it's equivalent to about 10 million volts per meter. Your cell membranes sustain electric fields stronger than those that cause air to break down and spark. This resting potential exists because neurons actively pump ions, charged particles, across their membranes. They push positively charged sodium ions out, and bring positively charged potassium ions in, but not in equal numbers. The result is an electrical imbalance, with the inside of the cell more negative than the outside. It's like each neuron is a tiny battery, constantly recharged by molecular pumps that consume about a third of your brain's energy budget just to maintain this electrical readiness. When a neuron decides to fire, perhaps because you've just seen a piece of chocolate cake and your brain is processing this vital information, something spectacular happens. Ion channels in the membrane suddenly open, allowing sodium to rush in. This makes the inside of the cell less negative, which causes more channels to open, which lets in more sodium, creating a cascade effect. The electrical potential rapidly reverses, shooting up to about 140 millivolts, before potassium channels open to restore the balance. This electrical wave, called an action potential, races down the neuron's axon at speeds that would impress any electrician. In your fastest neurons, signals travel at about 120 meters per second. That's over 250 miles per hour. The signal moves as a wave of opening and closing ion channels, like a stadium wave of molecular proportions. When it reaches the end of the neuron, it triggers the release of chemical messengers that carry the signal to the next neuron. It's an elegant dance between electrical and chemical signaling that happens billions of times every second in your brain. But here's what's truly remarkable. This isn't just random electrical noise. These patterns of electrical activity are your thoughts, your memories, your very consciousness. When neuroscientists use EEG to record brain activity, they're literally reading the electrical signatures of your mind. Different mental states produce different patterns. The slow, rolling waves of deep sleep, the rapid, complex patterns of problem solving, the synchronized rhythms of meditation. Your heart, too, runs on electricity, though in a more rhythmic fashion than your brain. Specialized pacemaker cells in your heart generate regular electrical impulses about 60 to 100 times per minute. Less if you're very fit, more if you've just seen your electricity bill. These impulses spread through your heart muscle in a carefully coordinated wave, causing the chambers to contract in sequence. An electrocardiogram, ECG or EKG, records this electrical activity from the surface of your skin. Each heartbeat produces a characteristic pattern, the P wave as your atria contract, the QRS complex as the main pumping chambers fire, and the T wave as they reset. Doctors can read these electrical hieroglyphs to diagnose everything from heart attacks to irregular rhythms. It's like your heart is constantly writing its autobiography in electrical ink. When this electrical system malfunctions, the results can be serious. Arrhythmias occur when the electrical signals become chaotic or blocked. Atrial fibrillation, where the upper chambers quiver instead of beating properly, affects millions of people. Ventricular fibrillation, where the main chambers lose coordination, is immediately life-threatening. This is why defibrillators exist. They deliver a strong electrical shock that essentially reboots your heart's electrical system, hopefully restoring normal rhythm. But why do electric shocks shock? When external electricity enters your body, it doesn't respect your carefully maintained cellular boundaries. Instead of flowing through designated channels, it takes whatever path offers least resistance, often through your bodily fluids, which are full of dissolved ions. This foreign current can overwhelm your body's electrical systems, causing muscles to contract involuntarily, which is why people can be frozen to electrical sources, disrupting your heart's rhythm or damaging tissues through heating. The amount of current matters more than voltage when it comes to electrical safety. A static shock from a doorknob might involve thousands of volts but almost no current, so it's merely annoying. But even small currents can be dangerous if they flow through your body. As little as 0.001 amperes across your heart can trigger fibrillation. Household current at 0.015 amperes or more can cause muscles to freeze, making it impossible to let go of an electrical source. This is why ground fault circuit interrupters, GFCIs, those outlets with the test and reset buttons in your bathroom, are so important. They detect even tiny currents flowing where they shouldn't and cut power in milliseconds. Your skin is actually your body's main electrical defense. Dry skin has high resistance, about 100,000 ohms, which limits how much current can flow. But wet skin drops to about 1,000 ohms, making you much more vulnerable to electrical shock. This is why you should never handle electrical devices with wet hands or in the bathtub. Your mother was right about that, as mothers often are about safety matters. Let's return to more pleasant electrical phenomena, like the static electricity that makes your hair stand on end. When you pull off a wool sweater on a dry day, you're literally ripping electrons from one material to another. The sweater might gain electrons and become negative, while your hair loses electrons and becomes positive. Since like charges repel, each positively charged strand of hair tries to get as far as possible from its neighbours, resulting in that Einstein-inspired hairdo. Children's science museums love demonstrating this with Van de Graaff generators, those metal spheres that make your hair stand up when you touch them. The generator continuously deposits charge on the sphere, and when you touch it while standing on an insulating platform, you become part of the charge system. Your hair strands, all carrying the same charge, repel each other like tiny magnets with the same poles facing. It's harmless but dramatic, though you might want to avoid touching grounded metal objects until you discharge. Speaking of static, have you ever wondered why balloons stick to walls after you rub them on your hair? The balloon steals electrons from your hair, becoming negatively charged. When you bring it near a wall, it repels the electrons in the wall's surface, leaving a positively charged area. The attraction between the negative balloon and the positive area of the wall is strong enough to overcome gravity, at least until air humidity gradually neutralizes the charge. Your body generates static electricity constantly as you move. Walking across a carpet can build up thousands of volts of potential difference between you and ground. The shock you feel touching a doorknob is actually a tiny lightning bolt, the air breaking down and conducting as electrons jump the gap. In very dry conditions, you might even see the spark. Some people are electric than others, generating static more easily due to their body chemistry, clothing choices, or gait. But beyond these obvious electrical effects, your body uses electricity in subtler ways. Your cells maintain electrical gradients across their membranes, using them to control what enters and exits. Your inner ear uses electrical signals to sense sound and balance. Your retina converts light to electrical impulses. Even your sense of taste and smell ultimately rely on electrical signaling to communicate chemical information to your brain. There's growing evidence that many biological processes we thought were purely chemical have electrical components. Wound healing appears to be guided partly by electrical fields. Damaged tissue generates electrical signals that attract repair cells. Some researchers are exploring whether cancers have different electrical properties than healthy tissue, potentially offering new diagnostic tools. Bone growth responds to electrical stimulation, which is why some difficult fractures are treated with electrical devices. Your body even generates electromagnetic fields that extend beyond your skin. The electrical activity of your heart produces a magnetic field that can be detected several feet away with sensitive instruments. Some researchers speculate that this might explain the feeling of someone standing close behind you, or the sense of personal space. You might literally be detecting the electromagnetic presence of others, though this remains scientifically controversial. Athletes and physical therapists have long used electrical stimulation for training and recovery. TENS units, transcutaneous electrical nerve stimulation, use electrical pulses to block pain signals. Electrical muscle stimulation can maintain muscle tone in paralyzed patients or help athletes recover from intense training. It's like hijacking your body's electrical system for therapeutic purposes. But perhaps the most profound human electrical connection is in how we interface with our technology. Every touchscreen tap, every keyboard press, every mouse click is ultimately an electrical connection between your biological circuits and silicon ones. Capacitive touchscreens work by detecting the electrical properties of your finger. Computer keyboards complete electrical circuits with each keystroke. Even voice assistants convert the mechanical vibrations of your speech into electrical signals for processing. We're increasingly becoming cyborgs, not in the science fiction sense of mechanical implants, but in how intimately our electrical systems interact with artificial ones. Prosthetic limbs can now be controlled by electrical signals from remaining nerves. Cochlear implants convert sound to electrical signals that directly stimulate the auditory nerve. Deep brain stimulation uses electrical pulses to treat conditions from Parkinson's disease to severe depression. The future promises even more intimate electrical connections. Brain-computer interfaces aim to read the electrical patterns of thought directly, potentially allowing paralyzed individuals to control computers or prosthetics with their minds. Scientists have already demonstrated systems that can decode simple intentions from brain activity. It's early days, but the possibility of direct electrical communication between brains and machines is no longer pure science fiction. There's something profound about realizing that the same force that powers your thoughts also lights your room. The electricity in your neurons follows the same fundamental laws as the electricity in your walls. You're not separate from the electrical world. You're part of it, a biological circuit in the grand electrical network of the universe. Your body maintains its electrical systems with remarkable precision. Too much or too little electrical activity in your brain can cause seizures. A small error in your heart's electrical timing can be fatal. Yet most of the time, this incredibly complex electrical orchestra plays on without your conscious awareness or intervention. Neurons fire, hearts beat, cells maintain their electrical gradients, all in a dance of ions and voltages that began before you were born and will continue until your last breath. So yes, you are electric. Every thought, every heartbeat, every movement is an electrical event. You're a walking, thinking, feeling manifestation of the same electromagnetic force that lights stars and powers civilization. The next time you flip a light switch, remember, you're not just using electricity, you are electricity channeled through flesh and blood, animated by the same fundamental force that flows through copper wires and silicon chips. In a very real sense, consciousness itself might be an electrical phenomenon, not reducible to mere electrons and voltages, but impossible without them. We are electrical beings in an electrical universe. brief patterns of organised energy contemplating our own existence. And if that's not a profound connection to the cosmic forces around us, I don't know what is. The future of electricity doesn't hum with the steady drone of massive power plants. It whispers in the rustle of leaves converting sunlight, whooshes with the turning of wind turbines, and crackles in the chemistry of ever-improving batteries. We're in the midst of an electrical revolution as profound as Edison's light bulb or Tesla's alternating current. But this time it's not about generating more power. It's about generating it more cleverly, storing it more efficiently, and using it more wisely. Let's start with the star of our solar system, that giant fusion reactor in the sky that bathes Earth with more energy in 1 hour than humanity uses in a year. Solar panels, more properly called photovoltaic cells, are humanity's attempt to catch this bounty, and they do it through a quantum mechanical sleight of hand that would have seemed like magic a century ago. Inside a solar cell, photons from the sun knock electrons loose from silicon atoms, creating electron-hole pairs. Remember those PN junctions from our semiconductor discussion? A solar cell is essentially a large PN junction designed to separate these electrons and holes before they can recombine. The built-in electric field at the junction pushes electrons one way and holes the other, creating a current. It's like a water wheel for light, converting the flow of photons into a flow of electrons. The efficiency of this conversion has been creeping upward for decades. The first practical silicon solar cells in the 1950s converted about 6% of sunlight to electricity. Today's commercial panels reach 20-22%, with laboratory cells pushing past 26%. Multi-junction cells, which stack different semiconductors to catch different colours of light, have exceeded 47% efficiency in lab conditions. It's like evolving from catching rain in a thimble to using a proper bucket. But efficiency is only part of the story. The real revolution has been in cost. Solar panels that cost $76 per watt in 1977 now cost less than just 20 lire per watt. In many parts of the world, solar is now the cheapest source of electricity, cheaper than coal, gas, or any fossil fuel. Vast solar farms spread across deserts like technological flowers, while rooftop panels turn millions of homes into tiny power plants. The intermittency problem, the sun inconveniently refusing to shine at night, is being tackled with increasingly creative solutions. Some solar thermal plants store heat in molten salt, which can generate steam for turbines hours after sunset. Others are paired with batteries, creating hybrid plants that can deliver power on demand. There's even research into space-based solar power, where satellites would collect sunlight above the atmosphere and beam energy down to Earth as microwaves. It sounds like science fiction, but the physics is sound. It's the economics that need work. Wind power, solar's breezy cousin, has undergone its own quiet revolution. Modern wind turbines are engineering marvels, with blades longer than football fields sweeping circles in the sky. The largest offshore turbines can generate 15 megawatts each, enough to power thousands of homes. They're so efficient at extracting energy from moving air that they're approaching the BETS limit, the theoretical maximum efficiency for wind turbines. The physics of wind power is beautifully simple. Moving air turns blades, blades turn generators, generators make electricity. But the engineering is fiendishly complex. The blades must be light yet strong, able to withstand hurricane-force winds while turning smoothly in a breeze. The generators use powerful permanent magnets made from rare earth elements, creating intense magnetic fields that efficiently convert rotation to electricity. Sophisticated control systems adjust blade pitch and turbine direction to maximize power while preventing damage in storms. Offshore wind farms are pushing into deeper waters where winds are stronger and more consistent. Floating turbines, anchored to the seabed but not fixed to it, can operate in waters too deep for traditional foundations. Some proposals envision vast floating wind farms far out to sea, where visual impact is nil and winds are powerful and steady. The engineering challenges are immense, Imagine maintaining equipment in the middle of the ocean, but the energy potential is enormous. But perhaps the most crucial technology for our electrical future isn't about generation, it's about storage. Batteries are the unsung heroes of the electrical revolution, and they're improving at a pace that would make Moore's law jealous. The lithium-ion battery in your phone has about 10 times the energy density of the lead-acid battery in your car, and costs have plummeted by 97% since 1991. Inside a lithium-ion battery, lithium ions shuttle between two electrodes through an electrolyte. During discharge, lithium ions move from the negative electrode, usually graphite, to the positive electrode, typically a lithium metal oxide, releasing energy. Charging reverses the process. It's like a very organised game of ionic musical chairs, with electrons flowing through the external circuit to balance the charge. The chemistry sounds simple, but the details are devilishly complex. Researchers tweak electrode materials, electrolyte compositions and cell designs to squeeze out more capacity, faster charging, longer life, and better safety. Silicon anodes can store more lithium than graphite, but tend to crack from expansion. Solid-state electrolytes could be safer than liquids, but are harder to manufacture. Every improvement involves trade-offs, like a multi-dimensional puzzle, where adjusting one piece affects all the others. Grid-scale batteries are transforming how we think about electricity. Massive installations, some covering acres, can store excess renewable energy and release it when needed. South Australia's Hornsdale Power Reserve, initially mocked as the world's biggest battery, has saved consumers millions by responding to grid fluctuations in milliseconds. It's like having a giant electrical shock absorber that smooths out the bumps in supply and demand. But lithium-ion isn't the only game in town. Flow batteries pump liquid electrolytes through cells, allowing capacity to be scaled simply by using bigger tanks. Sodium-ion batteries use abundant materials instead of scarce lithium. Solid-state batteries promise higher energy density and better safety. There's even research into aluminum-air batteries that could theoretically store as much energy as gasoline. The dream of wireless power, first envisioned by Tesla over a century ago, is inching toward reality. Your electric toothbrush probably charges wirelessly already, using electromagnetic induction. The same principle, scaled up, is being used for wireless phone charging and even electric vehicle charging pads. Put your car in the garage and it starts charging automatically. No plugs required. But modern wireless power goes beyond simple induction. Resonant inductive coupling can transfer power efficiently over distances of several meters. Researchers have demonstrated wireless power transfer to devices implanted in the body, potentially eliminating the need for battery replacement surgery. There are even proposals for satellite-based power beaming, though the efficiency and safety challenges remain formidable. The holy grail of energy generation remains fusion power, creating miniature stars on Earth. Fusion promises abundant clean energy, with no long-lived radioactive waste and fuel extracted from seawater. The physics is well understood. Heat hydrogen isotopes to hundreds of millions of degrees, and they'll fuse into helium, releasing energy. The engineering is the hard part. The challenge is containing something hotter than the centre of the sun. Since no material can withstand such temperatures, fusion reactors use magnetic fields to suspend the plasma in a magnetic bottle. Projects like ITER in France use superconducting magnets to create fields 200,000 times stronger than Earth's. It's like trying to hold jello with rubber bands, if the jello were at 100 million degrees and wanted desperately to escape. Recent breakthroughs have rekindled fusion optimism. In 2022, the National Ignition Facility achieved fusion ignition, getting more energy out than the lasers put in. Private companies are pursuing smaller, more innovative designs. Some use spherical tokamaks, others try inertial confinement, and a few explore exotic approaches like field-reversed configurations. It's a fusion renaissance, with dozens of approaches competing to be first to commercial viability. But fusion faces what's known as the fusion constant, the joke that fusion is always 20 years away and always will be. The engineering challenges are immense. materials that can withstand neutron bombardment, superconducting magnets that operate reliably for decades, plasma control systems that can prevent disruptions. Yet progress continues, driven by the tantalizing promise of nearly limitless clean energy. Smart grids are revolutionizing how electricity flows from generators to users. Traditional grids are one-way streets. Power flows from plants to consumers. Smart grids are more like the internet, with two-way communication and power flow. Your solar panels can feed excess power back to the grid. Your electric car can act as a mobile battery. Smart meters communicate real-time usage, allowing dynamic pricing that encourages conservation during peak times. Artificial intelligence is increasingly managing these complex systems. AI algorithms predict demand, optimize generation, route power efficiently, and detect problems before they cause outages. It's like having a brilliant conductor orchestrating millions of instruments in real time, ensuring the electrical symphony never misses a beat. Microgrids take this concept further, creating semi-autonomous electrical islands that can operate independently if needed. A university campus, military base, or neighborhood might have its own microgrid with local generation and storage. During normal times, it's connected to the main grid. During emergencies, it can island itself and keep the lights on. It's electrical resilience through decentralization. The electrification of everything continues apace. Electric vehicles are just the beginning. Electric aircraft are taking to the skies, starting with small planes but eyeing larger passenger jets. Electric ships are plying waterways. Even industrial processes traditionally dependent on fossil fuels, steelmaking, cement production, chemical manufacturing, are finding electrical alternatives. Heat pumps, those thermodynamic marvels that can move heat against its natural flow, are replacing gas furnaces and boilers. They're essentially air conditioners running in reverse, using electricity to concentrate heat from outside air even when it's cold. Modern heat pumps can extract useful heat from air at 15 degrees, seeming to violate common sense but obeying the laws of thermodynamics perfectly. Energy harvesting technologies are finding electricity in unexpected places. Piezoelectric materials generate electricity from mechanical stress. Imagine sidewalks that generate power from footsteps or roads that harvest energy from passing cars. Thermoelectric materials convert temperature differences directly to electricity. Even ambient radio waves can be harvested for tiny amounts of power, enough to run simple sensors. As we electrify our world, we're also discovering new ways to use electricity more efficiently. LED lights use 1/10 the energy of incandescent bulbs. Variable speed motors adjust their power consumption to match the load. Power electronics, those often overlooked devices that convert and control electrical power, have become incredibly efficient, wasting less than 5% of the energy they handle. The future of electricity isn't just about making more of it, it's about using it more intelligently. It's about buildings that generate their own power, vehicles that store and share it, grids that think and adapt, and devices that sip rather than gulp energy. It's about finally fulfilling electricity's promise as a clean, flexible, universal form of energy that powers civilization without destroying the planet that hosts it. We're witnessing the dawn of what might be called the electron economy, where electrical energy becomes as fluid and tradable as information. Your car might sell power back to the grid during peak hours. Your home might negotiate with appliances about when to run based on electricity prices. Communities might share power peer-to-peer, like file sharing but for electrons. The challenges remain immense. Rare earth elements for batteries and motors are, well, rare. The grid infrastructure in many countries is aging and ill-equipped for bidirectional power flow. Intermittent renewables require massive overbuilding or storage to ensure reliability. But human ingenuity has a way of finding solutions, especially when the problems are clearly defined and the stakes are high. As we stand on the brink of this electrical transformation, it's worth remembering that every previous electrical revolution seemed impossible until it wasn't. Who would have believed watching Franklin fly his kite that we'd one day light entire cities with electricity? Who could have imagined, seeing Faraday's first crude generator, that we'd power our civilization by spinning magnets? The future of electricity will likely surprise us too, in ways we can barely imagine from our current vantage point. Stop for a moment and try to imagine your day without electricity. The alarm that didn't ring, the coffee that didn't brew, the phone that didn't charge, the car that might not start. Even gas cars need electricity for ignition. The traffic lights that don't work, the elevators that don't rise, the internet that doesn't exist. It's not just that modern life would be inconvenient without electricity, it would be unrecognisable. We've woven electrons so thoroughly into the fabric of our existence that removing them would unravel civilization itself. But the depth of our electrical dependence goes far beyond the obvious. Consider the hidden electrical world humming away in places you'd never think to look. Your refrigerator isn't just cooling, it's running a complex dance of compressors, fans and sensors, all coordinated by a small computer that would have been considered a supercomputer decades ago. That computer monitors temperatures, adjusts cooling cycles, defrosts when needed, and even tracks door openings to optimize efficiency. Your washing machine is another secret genius. Modern washers contain multiple motors, pumps and valves, all orchestrated by sophisticated electronics. They sense load size, adjust water levels, modify agitation patterns, and even detect fabric types. Some can diagnose their own problems and order replacement parts. It's like having a very specialized robot that happens to be shaped like a large box and dedicated to cleaning fabric. The electrical intelligence embedded in everyday objects would seem miraculous to someone from just 50 years ago. Your television isn't just displaying pictures, it's decoding complex digital signals, upscaling lower resolution content, adjusting brightness based on room lighting, and possibly listening for voice commands. Your thermostat learns your schedule, predicts your preferences, and negotiates with your power company for better rates. Even your light bulbs might be smart, changing color temperature throughout the day to support your circadian rhythms. This proliferation of electrical intelligence, the Internet of Things as marketers call it, means that dozens or hundreds of devices in your home are constantly communicating. They form an invisible network of chatter, exchanging data about temperatures, pressures, motion, light levels, and countless other parameters. Your home has become a living organism with an electrical nervous system, sensing and responding to conditions in real time. But what happens when the power goes out? The silence is profound. Not just the absence of humming appliances, but the sudden cessation of the electrical heartbeat that normally permeates our spaces. No more barely audible high-frequency whines from chargers and power supplies. No more soft electromagnetic fields from hidden wiring. It's as if the house itself has stopped breathing. Power outages reveal our electrical vulnerability in stark terms. Food spoils in warming refrigerators. Basements flood without sump pumps. Medical equipment fails without backup power. Communication networks collapse as cell towers exhaust their batteries. The elderly and ill suffer without heating or cooling. Modern life doesn't gracefully degrade without electricity, it simply stops. Yet we're remarkably adapted to this electrical ecosystem. Most of us navigate dozens of electrical interactions daily without conscious thought. We know intuitively how long to microwave leftovers, when our phone needs charging, which remote controls which device. We've developed an electrical intuition, a sixth sense for the flow of electrons through our environment. Children today grow up natives of this electrical world. They swipe touch screens before they can write, understand charging cables before they can tie shoes, and navigate digital interfaces with an ease that can astound their grandparents. They're not just using electrical devices. They're thinking in electrical terms, understanding the world through the lens of connectivity, battery life, and signal strength. Our digital consciousness, the part of us that exists in email, social media, cloud storage, and countless databases, is entirely electrical. Every photo you've taken, every message you've sent, Every search you've made exists as patterns of electrical charge in server farms around the world. When you video call someone on the other side of the planet, your words and image are converted to electrical pulses that race through fiber optic cables and bounce off satellites, reassembling into sound and light thousands of miles away. You're not just using electricity, you're being translated into it, transmitted, and reconstituted. The cloud, that nebulous term for distributed computing, is really just other people's computers running in vast data centers. These electronic cities consume electricity on a staggering scale. A single large data center might use as much power as a small city, all to maintain the illusion that your data is somehow floating weightlessly in cyberspace. Every Google search, every streamed video, every liked photo requires electrons to flow through silicon pathways, generating heat that must be removed by more electricity-hungry cooling systems. Cryptocurrency mining has created a bizarre new relationship with electricity. Vast warehouses full of specialized computers burn through gigawatts of power, solving mathematical puzzles to mint digital coins. It's alchemy in reverse, turning electrical energy into digital gold. Some mining operations chase cheap electricity around the globe like digital nomads, setting up shop wherever rates are lowest or excess power needs using. Our entertainment too has become thoroughly electrical. The shift from physical media to streaming means that watching a movie now requires a constant flow of electrons from distant servers to your screen. Video games render entire worlds in real time, with graphics processors performing trillions of calculations per second. Virtual reality promises, or threatens, to make the electrical world even more immersive, creating synthetic realities indistinguishable from the real. But it's not just our digital lives that depend on electricity. Modern agriculture uses GPS-guided tractors, automated irrigation systems, and climate-controlled greenhouses. Food processing plants rely on electrical machinery for everything from sorting apples to packaging pasta. The global food system would collapse without refrigeration, which preserves food from farm to table. Even traditional-seeming farms often harbour surprising electrical complexity. Automated milking systems, egg collectors, feed dispensers, all choreographed by computers. Medicine has become unimaginable without electricity. Beyond the obvious, MRI machines, X-ray equipment, surgical tools, there's the hidden electrical infrastructure. Electronic health records, automated pharmacy systems, infusion pumps that precisely deliver medications, ventilators that breathe for patients. During the COVID-19 pandemic, the shortage of ventilators highlighted how a relatively simple electrical device, a pump that moves air, can mean the difference between life and death. Our understanding of the world itself depends on electrical instruments. The Large Hadron Collider uses superconducting magnets and incredible electrical power to accelerate particles to near light speed. The Hubble Space Telescope and its successors translate faint photons into electrical signals, revealing the cosmos. Climate monitoring stations around the world electrically measure temperatures, pressures, and gas concentrations, building our picture of a changing planet. Even activities that seem untouched by modernity often have electrical components. That acoustic guitar performance, probably amplified through an electrical sound system. The artisanal bread from your local bakery, mixed by electric motors and baked in electrically controlled ovens. The scenic hiking trail, maintained by crews using electric tools and navigating with GPS. We've created an electromagnetic ecosystem that overlays the natural world. Radio waves from countless sources, cell towers, Wi-Fi routers, broadcast stations, satellites, create an invisible landscape of signals. If our eyes could see radio frequencies, the air would shimmer with constant activity, like being inside an aurora that never ends. We've painted the electromagnetic spectrum with our transmissions, filling previously quiet frequencies with the chatter of civilization. This electrical saturation has consequences. Light pollution from our electrically lit cities obscures the stars for most of humanity. Electromagnetic interference can disrupt sensitive equipment. There are concerns about the health effects of constant exposure to electromagnetic fields, though the scientific consensus suggests typical exposure levels are safe. Still, we're conducting a vast experiment, bathing ourselves in artificial electromagnetic radiation to a degree unprecedented in human history. The pace of electrical change continues to accelerate. Artificial intelligence, which requires vast amounts of computational power and therefore electricity, is beginning to manage more aspects of our lives. Quantum computers, operating at temperatures near absolute zero, promise to solve problems beyond the reach of classical computers. Brain-computer interfaces might one day merge our biological electrical systems with artificial ones in ways we can barely imagine. Yet for all this complexity, the fundamental nature of electricity remains unchanged. Electrons still flow from negative to positive. Magnetic fields still induce currents, and Ohm's law still governs resistance. We've built a civilization of staggering electrical complexity on foundations discovered 2 centuries ago. It's as if we've constructed a digital cathedral using blueprints written by Franklin and Faraday. The resilience of our electrical civilization is constantly tested. Solar storms can induce currents in long power lines, potentially damaging transformers. Cyber attacks target electrical infrastructure, seeking to disrupt the flow of power and information. Climate change brings more extreme weather that batters the physical infrastructure of our electrical networks. Yet somehow, the lights mostly stay on, the devices keep working, and the electrical pulse of civilization continues. As we face challenges like climate change, inequality, and resource depletion, electricity offers both problems and solutions. The production of electricity still relies heavily on fossil fuels in many places, contributing to greenhouse gas emissions. The mining of materials for batteries and electronics can be environmentally destructive. Electronic waste is a growing problem as devices become obsolete ever faster. But electricity also enables solutions. Renewable energy, electric transportation, efficient lighting and heating all depend on our mastery of electrons. Smart grids can reduce waste. Electric recycling technologies can recover valuable materials. The same force that powers our problems might also power our salvation. We stand at an electrical crossroads. We can continue the unsustainable electrification of everything, burning through resources and energy without thought for the future. Or we can use our electrical mastery more wisely, creating systems that work with rather than against natural cycles. The choice is ours, but it must be made consciously, with full awareness of our deep dependence on the invisible river of electrons that flows through our lives. The story of electricity is really the story of human ingenuity, curiosity, and ambition. From the ancient Greeks rubbing amber to modern engineers designing quantum computers, we've pursued the dream of understanding and harnessing this fundamental force. We've succeeded beyond the wildest dreams of the pioneers who first glimpsed electricity's potential. But with great power, electrical and otherwise, comes great responsibility. And here we are, at the end of our electrical odyssey, though in truth the current never really stops flowing, does it? We've travelled from the amber experiments of ancient Greeks to the quantum computers of today, from lightning bolts to LEDs, from electric eels to the electrical storms in your own brain. What a journey it's been, following the path of electrons as they dance through our world and our lives. I wonder, as you prepare to close your eyes tonight, what electrical devices surround you in this moment. Perhaps the soft glow of a phone screen casting its blue light one last time before sleep. Maybe the gentle hum of a fan circulating air, or the quiet tick of a digital clock marking the seconds. The electricity that has accompanied us throughout this tale continues its quiet work, faithful as a heartbeat, reliable as the tide. It's remarkable, isn't it, how something so fundamental can be so invisible? We've learned that electricity isn't just in our devices, it's in us, animating our thoughts, driving our hearts, sparking the very essence of life itself. Every word you've heard tonight travelled as electrical impulses through neurons before becoming meaning in your mind. Even now, as drowsiness perhaps begins to settle over you like a comfortable blanket, electrical patterns in your brain are shifting, slowing, preparing for the mysterious electrical symphony of sleep. What will you unplug tonight before bed? Your phone from its charger perhaps, now fully fed with electrons for tomorrow's adventures. Maybe you'll switch off a lamp, breaking the circuit that brings photons to push back the darkness. Or perhaps you'll leave something charging, trusting in the steady flow of current to prepare your devices for another day. These simple acts, plugging in, switching off, connect you to power plants miles away, to the turning of turbines, to the fundamental forces that govern the universe. We've discovered that electricity is both particle and wave, both incredibly powerful and exquisitely controllable. It's the lightning that splits the sky and the gentle current in a butterfly's antennae. It's ancient beyond measure, present in the first moments after the Big Bang, yet fresh and immediate in every moment of our modern lives. What a privilege it is to live in an age where we've learned to conduct this cosmic force, to invite it into our homes and devices and very bodies. Tomorrow, when you flip that first switch of the day, perhaps you'll think differently about what happens. Not just bulbs lighting or motors spinning, but billions of electrons responding to your command, electromagnetic fields rippling into existence, energy transforming from one form to another in an endless dance. You're not just using electricity, you're participating in one of the universe's fundamental phenomena. But for now, as the hour grows late and the electrical activity in your brain naturally slows, preparing for the restorative rhythms of sleep, let's appreciate the gentle current that surrounds us. Somewhere, power plants are humming, their generators turning steadily to maintain the electrical heartbeat of civilization. Electrons are flowing through countless circuits, carrying information, light, heat, and the myriad blessings of our electrical age. The electrical world will continue its work while you sleep. Refrigerators will cycle on and off, maintaining the cold. Phones will receive messages in the darkness. Servers around the world will tend to humanity's digital dreams, and in your own body, electrical impulses will continue their ancient work, maintaining heartbeat, orchestrating breath, weaving the mysterious electrical patterns of dreams. So as you prepare to drift off, remember that you're never really disconnected from the electrical web of existence. You're part of it, a biological circuit in the grand electrical network of the universe. From the electrons spinning in every atom of your being to the electromagnetic waves carrying signals across the cosmos, you're intimately connected to the same force that lights the stars and powers our dreams of the future. Sleep well, dear listener, surrounded by the gentle current that powers our world. May your dreams be filled with the soft glow of understanding, and may you wake tomorrow with a renewed appreciation for the invisible force that makes so much of modern life possible. The electrons will continue their eternal dance, and will continue ours, partners in the grand electrical ballet of existence. Thank you for joining me on this journey through the world of electricity. From amber to atoms, from lightning to LEDs, from the spark of life to the power of tomorrow. What an adventure it's been. Until next time, when perhaps we'll explore another wonder of our remarkable universe, this is Science for Sleep, signing off with a gentle electrical whisper, sweet dreams and good night.